Assalamualaikum warahmatullahi wabarakatuh. Hello, my name is Pramudito Bagas Umboro. I am from the class Fluid Mechanics 03. In this video, I will be explaining my answers to the final exam of Fluid Mechanics. So the content in this video will be a problem about the flow through an orifice meter, problem about a flow in an irrigation system, a problem about the deceleration of an automobile by a drag parachute, a problem about the flow in open channel, and a problem about the choked flow in a converging nozzle. So the first problem is flow through an orifice meter. So my intention is to apply my knowledge gifted by God to define the exact requirements, finding the orifice diameter and calculating head loss, ensuring clarity on units and conditions. In initial thinking, given the airflow rate, duct diameter, manometer range, and the vena contracta are shown, so I need to convert the manometer reading into a pressure drop and use Bernoulli's equation along with the orifice flow equation. And the idealization is we assume that the density of the air is 1.23 kilogram per meter cube per cube meter, and the viscosity is 1.46 times 10 to the power of -5. And we use standard fluid dynamics equations to relate flow rate, pressure drop, and orifice diameter. And then in instruction, we first must know the mass flow rates equation and then the pressure change and also the height of water column in manometer. And then we apply it to Reynolds number and we get 3.5 times 10 to the power of 5. And then we apply it to pressure change equation and water height. And we try the throat diameter of 0.165 and beta of 0.66. We use the head loss equation and then we assume these uh, these constants, and then hence we get the head loss into this equation, and then we assume a few more constances and assumption and boundaries, and then we simplify the equation that we had, and then we find the flow speed at 2, and we apply it to pressure change 3 and 2, and then we get the pressure change between section 3 and 2 equals to 1,290 newtons per square meter. And we apply it to head loss, and we get 1,250 Newton meter per kilogram. And then we find the head loss through the orifice, which is equal to 0.44. And so the total head loss through the orifice is around 44%. And the next problem is about the spray head. And my intention is to apply my knowledge gifted by God to determine the smallest standard pipe size to supply water through 500 feet of aluminum tubing, ensuring sprinklers operate at 30 psig or higher. Initial thinking, given the flow rate, the pump output pressure, required sprinkler pressure, minor losses, and elevations are neglected. Then we use the Darcy-Weisbach equation to relate pressure drop, pipe length, diameter, and flow rate. And then in idealization, we assume an initial friction factor for smooth aluminum tubing and convert the flow rate from gallons per minute to cubic feet per second. And then delta P, L, and Q are known, D is unknown, so iteration is needed to determine the minimum standard diameter that satisfies the pressure drop constraint at the given flow rate. So instruction is our execution of the plan. We find the maximum pressure change, we get 35 psi, and then we simplify the head loss equation, and then we assume the boundaries and constances, and then we simplify the pressure change after we apply several other equations. And then we also apply Reynolds number in terms of Q, and then the flow rate, we find it by changing from gallons per minute to cube feet per second. And then we input D equals 6-inch and 5-inch. And then we get that the 6-inch diameter shows that it has a pressure change under the maximum pressure change, and the one with the 5-inch diameter has a pressure change above the maximum pressure change, which means the minimum diameter for pressure drop is 6 inches. Next is the deceleration of an automobile by a drag parachute. My intention is to apply my knowledge gifted by God to determine the time required for a dragster to decelerate from 270 miles per hour to 100 miles per hour after deploying a drag chute. With the initial thinking of given that the initial speed is 270 miles per hour, final speed is 100, and the drag chute area is 25 feet squared, and then we neglect air and rolling resistance. We use drag force equation and Newton's second law to set up a differential equation for velocity. And then in idealization, we assume standard air density and formulate differential equation using Newton's law with density equal to 0.00238 slug per cubic feet. And then in instruction, since the drag coefficient equals to this, we find the drag force equals to half times drag coefficient times density times speed squared times area. And then we substitute into Newton's second law, and then we separate variables, and then we integrate it. And then first we find t, which we find t equals 5.05 seconds. And then we verify using Reynolds number, which shows that it is valid. And then the next problem is flow in open channels. My intention is to apply my knowledge gifted by God to determine the height of the wave at speed v. And then the initial thinking is the speed and everything affecting the height, the wave height is considered a constant and is uniform throughout the space. And then idealization, we assume steady flow, incompressible flow, uniform velocity at each section, hydrostatic pressure distribution at each section, and frictionless flow. And then in instruction, we apply these, and then we see that we see the end continuity equation, and then we apply it to control volume. And then to find the change in speed, we have this, and then we find the total height of wave, which is equal to c times delta y per delta v. And then the final question is the choke flow in a converging nozzle. And my intention is to apply my knowledge gifted by God to determine the Mach number at the throat, the mass flow rate, and the throat area for air flowing isentropically through a converging nozzle. With initial thinking given the Mach number equals 0.52, temperature 40 degrees Fahrenheit, we must convert to Rankine. Pressure 60 psi and nozzle area and also back pressure. And then we use isentropic flow relations and continuity equation. For idealization, we assume ideal gas behavior for air and convert temperature to Rankine. And then in instruction, we check the stagnation condition and then we check the back pressure ratio. And then we find the Mach number, and then we see the Mach number is 1.0, and we see the flow speed at 1 equals 570 feet per second. And then we see the density at 1 equals to 0.324 pound per cube feet. And then we find the mass flow rate, and then we use the isentropic process, and we see that the area ratio is 1.303. And then we find the throat area equals to 9.98 times 10 to the power of negative 3 square feet. Thank you. That is all from my video. Forgive me for any mistakes that I have made. Assalamualaikum warahmatullahi wabarakatuh. Stay conscious.